The sun often appears as a steady, reliable source of life, a smooth and peaceful sphere, but it is actually a chaotic, boiling ocean of plasma that can suddenly hurl radiation and matter in random directions. These events take two primary forms. Solar flares arrive as massive bursts of radiation, while coronal mass ejections, or CMEs, are gargantuan clouds of solar plasma that tear through the vacuum of the solar system. Most people on the surface will never feel these storms pass. While the biological world remains largely unaffected by this space weather, the complex electronics and power grids we rely on every day are far more sensitive. This risk is not a distant theoretical possibility. In 2012, a storm as powerful as the largest ever recorded missed Earth by only a small margin. Statistically, there is a 12% chance of a direct hit from a major solar superstorm every decade. Historically, these eruptions were visible only as silent lights in the night sky. However, our rapid transition to a society powered by millions of miles of electrical wiring has created a vulnerability that is now subject to the sun's unpredictable cycles. The sun's volatility is driven by a process called the dynamo. Because the sun is made of electrically charged plasma, its constant movement generates massive magnetic fields that twist and churn as the star rotates. These magnetic fields eventually become so kinked and tangled that they form magnetic knots. When these knots finally break, they release their stored energy explosively, similar to a cluster of tightly wound springs suddenly snapping outward. This release triggers the first wave of a solar storm, the flare. It is a tidal wave of high-energy radiation that travels at the speed of light, sweeping up particles in the solar wind as it races through the solar system. Following the flare is the coronal mass ejection. As seen in this imagery, a CME involves the sun catapulting billions of tons of its own atmosphere into space, sending a physical cloud of magnetic plasma toward the planets at millions of kilometers per hour. The sun isn't just emitting light, it is periodically acting as a cosmic cannon, firing physical clouds of magnetized matter directly into the orbits of the planets. This heavy cloud of plasma must cross a 150 million kilometer void to reach us. Even at its immense speed, it typically takes less than a day to complete the journey. Earth has a primary line of defense, the magnetosphere. This magnetic shield usually acts as a buffer, deflecting the electrified plasma of a CME toward the poles and away from the surface. If the magnetic field of the CME is aligned just right, it can merge with our own. The incoming solar energy stretches the Earth's magnetic field into a long, strained tail reaching far into space. When that tail can no longer contain the energy, it snaps. The stored energy releases explosively back toward the planet, funneling charged particles into our atmosphere. This dumping of energy causes the atmosphere to glow, creating the auroras we see near the poles. This is the visual signature of a geomagnetic storm in progress. This mechanism shows that our magnetic shield doesn't just block solar energy. Under the right conditions, it can actually capture and amplify the force of a solar storm. The benchmark for these events is the 1859 Carrington Event, the largest geomagnetic storm ever observed. It produced auroras so bright that people across the Americas thought the sun was rising in the middle of the night. At the time, our only major electrical technology was the telegraph. The shifting magnetic fields induced physical electric currents in these long copper wires, causing machines to spark, fail, and even shock their operators. Today, we have millions of kilometers of wires and a complex electrical grid. Within this grid are transformers like the ones shown here. A modern superstorm could induce massive currents capable of physically melting these critical stations. A direct hit today could cause a global failure of electronic systems. The resulting damage to our power and communication infrastructure could take years to repair, leading to a severe disruption of the global supply chain. Despite these risks, we are not helpless. Scientists monitoring the sun can detect a CME as it leaves the solar atmosphere, giving us a warning window of hours to days. This lead time allows for an engineering solution called preventative blackouts. If we know a storm is coming, we can temporarily shut down parts of the grid ourselves. Engineers can take transformers offline or open extra lines to dissipate the surge. By simply unplugging the world's most sensitive hardware, we allow the solar storm to pass over the grid without inducing the currents that cause physical destruction. We cannot prevent the sun from firing a monster storm our way, but our vulnerability to it is manageable. With early